Hi, today we're going to talk about imperfect squares, okay, and how we can estimate the value of imperfect squares. So, an imperfect square number is a number that's not a perfect square, as you might have guessed from the definition. So, for instance, 3, 5, 6 are not perfect squares. Remember, the definition of a perfect square is that it has two identical factors. 3 doesn't have identical factors. 1 I was thinking of 1 because 1 is actually, oddly enough, a perfect square. It's the first perfect square because 1 has identical factors of 1 in itself. So 1 is not an imperfect square number. It's actually a square number. But 3 is a prime, so it has no factors other than 1 in itself. 5 is 2. 6 is not a prime, but the factors are 2 and 3, so they're not identical, right? 2 and 3 are not the same number. So 3, 5, 6 are examples of things that are imperfect squares. The square root of imperfect squares are called irrational numbers, and we're going to talk about those a little bit more in the next section. So just hold off on the identification of irrational numbers. We're going to talk about them more later. But what you need to know are irrational numbers have decimal expansions that never terminate or they never repeat. Okay, they both do not terminate and they don't repeat. So another way of saying this is they don't terminate, and another property is that they don't repeat. Okay, so they don't do either one. Okay, because if something terminates, we can turn it into a fraction. If something repeats, like we saw before, we can also turn it into a fraction. If they don't do either one of them, then it's impossible. We can't turn it into a fraction. We can't turn it into a ratio. That's why this irrational means right? That prefix means that you cannot turn it into a ratio, right? It's part of what this word means. Some classic examples are pi, which is the ratio of a circle's circumference to its diameter. We cannot turn that into, it doesn't terminate, it doesn't repeat. The decimal expansion goes on and on forever and ever. When we take the square root of a number itself that is not a perfect square, we get these weird numbers, these weird irrational numbers too. Okay, the square root of 2 was the first one that was really sort of discussed in mathematics. And the square root of 5 quickly came afterwards, but it turns out that anytime you take the square root of a number that's not a perfect square, you get an irrational number. Since the decimal expansion of irrational numbers never terminate and they never repeat, we use symbols to represent irrational numbers. Okay, so a classic symbol is pi. Pi represents this number 3.14 ... because it goes on and on and on. But what pi is a letter in the Greek alphabet, so it's not as if pi didn't already represent something. We just use that symbol to represent in another system, in the math system, that it's a number that goes on and on and on. This is the most exact representation of a circle's circumference to its diameter, because if you tried to write down its decimal expansion, you'd at some point, of course, because you don't live forever and you're not going to write forever, you'd have to stop writing, right? That's just the rules of the game. Anytime you stop writing this digit, it's going to be an inexact number because it goes on and on, longer than you have time to ever write it. Okay, same thing with the square root of 5. Oddly, it's very, very strange that these numbers go on and never terminate and never repeat, and they sort of really freaked the mathematical world out when they were discovered. But nonetheless, we have to learn how to deal with them. So instead of writing this out as a decimal that doesn't terminate or repeat, we keep it, most often we like to keep it in the radical form. So we keep this radical symbol. By the way, this number underneath here is called the radicand. So the symbol itself is called the radical. Okay, and the word inside, for the number inside, is called the radicand. We say that this is radical 5, and this is the most exact form of this number. Now, it's not super helpful in terms of calculation, in terms of estimation. So what we're going to do today is we're going to talk about estimating the square roots of numbers. Now, in order to do that, we are going to use a sort of sandwiching technique. Okay, I am going to sandwich the square root of 5 in between the square roots of two perfect squares. Now, the first thing I want you to understand very quickly is that there's sometimes a misconception that students have. They say that the square root of 5 is equal to 5, and that is simply not the case. The square root of 5 is some number that when you multiply itself, it gets 5. 5 is the factors of 5 are 5 and 1, right? So this is very different. The square root of 5 is not equal to 5. It's less than 5, and you might be a little bit confused by that at first because we see this symbol here, and your mind quickly wants to say, oh, well, that's about 5, but it's not at all. It's very, very different. So let's take the square root of 5, and on either side, let's put the perfect squares, the square roots of the perfect squares that are close to 5. So 5 is between the perfect squares of 4 and 9. So I'm going to sandwich the square root of 5 between the square root of 4 and the square root of 9. Okay, so after I've done that, I'm going to think about my number line. Well, the square root of 4 is actually equal to 2, and the square root of 9 is actually equal to 3. So I know the square root of 5 lives between the numbers 2 and 3. Now think about the radicands for just a second, 4, 5, and 9, all right? 5 is closer to 4 than it is to 9, so that means that if 2.5 were here, the square root of 5 is going to be closer to 2 than it is to 3, so it's going to be on the left-hand side of 2.5. Okay, so it's going to be maybe about here, the square root of 5. And that's about as exact as you need to get it in 8th grade. Just, I want you to be able to tell me between which two integers it lies, and whether it lies to the left of the midpoint between the two integers or to the right of the midpoint, which is the halfway mark. Okay, so that's a good technique for estimating square roots. Let's say that you had to do a larger square root, like the square root of 72, for instance. Okay, so let's think about this. 81 is above it. That's 9, so 64 must be below it. So the square root of 72 is between 8 and 9, because the principal square root of 81 is 9, the principal square root of 64 is 8. Now let's think about the halfway mark, which would be 8.5. Let's see, the difference between the radicands 64 and 72 is 8, and the difference between 72, okay, this is 8, and the difference between 72 and 81 is 9. So it's all I'm doing here, not to confuse you, is this right here is 8, and then 81 minus 72 is 9. Okay, so what that means is that square root of 72 is going to be a little bit closer to 9 than to 8 rather than 9, but not that much closer, right? Because the differences between the radicands are not that great. All right, so right here is where square root of 72 resides. So to write that nice and neatly, I'd put a dot here, and then I'd write the square root of 72, or the principal square root of 72. Okay, so that's the way that you would graph this on a number line. You'd figure out, you use a sandwiching technique, using perfect squares around it to find the integers it lies between, and then you figure out whether it's to the left or to the right of the halfway mark. And that's it. Okay, and let me just show you how to quickly get them on the calculator here. This little button is the square root button. So I'm going to press that right here, and I'm going to ask the calculator to evaluate the principal square root of 72. And so you can see it's very close to 8.5, but it is less than 8.5, just like we thought it was going to be. So whenever you have to get the principal square root, you can just use the calculator to check it. Now remember that the decimal expansion here is going to never terminate and never repeat, because we know it's an irrational number. We know that because 72 is not a perfect square, and we're taking the square root of it. Anytime you do that, you're going to get a number that's imperfect, irrational. Now, with irrational numbers, anytime you write the numbers down, it's going to be an estimate. The most exact form of the number is to keep it in its radical form. So radical 72 is the only time you can write this number down where it's exact. Any other time you write it down, it's going to be an estimation. Okay, so if I say find the square root of 72, write it in decimal form and round it to the nearest hundredth, you would say it was 8.49, because the thousands place has a 5. If you round that to nearest hundredth, that would round up, right? Otherwise, you might be asked to keep it as radical 72, or this principal square root of 72, because that is literally the only way that you can write it so that it is exact. Any other way you write it, it's going to be inexact. Okay? And that's the end of the lesson for today.